Assalamu alaikum. Today we're going to talk about some circuit elements and we're going to start off our discussion with the famous capacitor. Now we all know that capacitors are ubiquitous. They exist in so many different kinds and forms. For example, we can have a parallel plate capacitor which comprises two plates of metals that are separated by some distance d. These plates can also be circular instead of being rectangular. We can have all kinds of capacitors. For example, we can have a coaxial capacitor which has a central conductor surrounded by an outer conductor, just like a coaxial cable. So if the inner conductor is charged, the outer conductor is charged, this object can store charge, and that's what a capacitor really is. Both of these plates can be charged. They can carry opposite charges. So this is a charge storage device. A metallic sphere of radius capital R that carries a charge plus Q. Of course, all of this charge is going to reside on the outer surface. This object also stores charge. It also acts like a capacitor. So there are different kinds of capacitors that we can come across. In radio circuits, in the old radio circuits, we had these circular capacitors in which we could rotate the orientation of one of the set of discs. So when you turn a knob, one of the set of discs rotates and the overlap area between the two plates changes. You electrically connect these plates together, and you connect these plates together. So such a capacitor is also called a variable air capacitor or a gang in the radio technologists community. So there are all different kinds of capacitors, and generally the circuit symbol that we employ for a capacitor is just two plates. We can also have a Swiss roll kind of capacitor in which a metal foil goes around in a circular fashion, and the other metal foil just surrounds this foil and is concentric with the first conductor, and each of these conductors is curled. You make a connection to this coiled wire and you make a connection to this coiled wire, and in between you could have air, or you could have some electrolyte, or you could have paper, mica, etc. So there are different kinds of capacitors that we can identify. But how does a capacitor really work? So what I would like to talk about now is first of all, a capacitor is a charge storage device. I would like to talk about the discharge of a capacitor, because this is something that's easy to understand. And I would like to describe the discharge of a capacitor in terms of electric fields. G.
How can there be an electrolyte?
Why not?
How will it?
How will it?
Shouldn't there be an insulator?
An electrolyte is also an insulator. So an electrolyte really means a dielectric. You can have, paper is also an electrolyte. There are charge carriers inside electrolytes. So electrolyte generally means a dielectric. Okay? It's a non-conducting material. Alright, so I would like to talk about the discharge of a capacitor first. Suppose I have a capacitor which comprises two parallel plates, and this capacitor carries a charge plus Q, which really means that one of these plates is positively charged, the charge on this is plus Q, and the other plate is negatively charged with the same amount of charge minus Q. So this is the initial condition of a capacitor. It has been charged. Some charge has been delivered to this capacitor somehow. Now we connect these parallel plates through a piece of wire. A thick piece of wire. Now this is not an infinite plate. We would like to see how does this object discharge, and what happens to the electric field inside this configuration. For convenience, I would like to draw a bulb here. A bulb is just a thin piece of wire. So I represent that bulb by a thin piece of wire. That's what really a bulb is. Okay? So it's a high resistor material. It's a highly resistive material. A thin filament is a high resistor. So it's represented in this schematic diagram by a thin piece of wire. Now what's going to happen is that an electric field is going to set up inside this object, inside this circuit, inside this piece of wire. Initially, there is electric field inside the gap. That electric field is pointing in this particular direction. Okay? And remember, this is a real capacitor. It's a finite sized capacitor. The plates are not infinitely sized. This electric field is approximately given by Q over A over epsilon naught, where A is the cross-sectional area of one of these plates. And why do I write approximation here? Because this is not an infinite parallel plate capacitor. Now since this is not an infinite capacitor, would there be any electric field set up inside the wire? Okay, if this were an infinite plate capacitor, would there be a field? If this were truly an infinite plate capacitor, then all the electric field is confined to within the gap. It cannot leak outside. But this is really like a dipole. So for a dipole, you will have a field that fringes outwards, an electric field that goes around like this. And at the other hand, there will also be an electric field here. There will also be an electric field here. So inside the wire, because of this charge distribution, these are real charges, electric fields will be set up. So just in the vicinity of this plate, near the wire, there will be an electric field inside the wire. This is called a fringe field. It's not an infinite plate. If it were an infinite plate, there would be no fringe field. But really, there is a fringe field here because of the finitude of these plates, because of the finite size of these plates. Now what's going to happen here is, the instant you connect the wire to this parallel plate capacitor, which has stored a charge plus Q, a fringe field will be set up in the wire. And this happens on the order of nanoseconds, because this information that the wire has been connected travels at the speed of light. And this is a small circuit. So in the order of picoseconds to nanoseconds, the electric field is going to be set up. Because in the wire, the electrons see an electric field. Now, under the action of that electric field, consider an electron here, which is a member of the sea of electrons. Okay, this is a member of the electron sea. Now this electron is going to be attracted towards this positive plate, or it will move in a direction opposite to the direction of the applied field. So electrons will rush towards this positive plate, which will cause a depletion of electrons in this region. So on this surface of this conductor, a positive charge is going to be set up, just as if we've connected a battery to a wire. So surface charges will be distributed on the surface of this circuit, just as if we've connected a battery to a circuit, and we'll discuss this in detail. So this surface charge will actually dilute itself from the positive to the negative end. So here there will be some surface charge. It will dilute as we go away from this positive plate. Here there's going to be some negative charge. This negative charge is going to concentrate a little bit as we move towards the negative plate. So under the action of the electric field that is set up inside the wire, because of this outward propagation of information that the wire has been connected to the capacitor, local electric fields are set up because of this charge gradient. And this charge gradient is produced because of the fringe field of the capacitor. And this information propagates outwards from the capacitor to all throughout the circuit. So an electric field is going to be set up all around the wire. The field is going to be the same, uniform in magnitude to the thick section of the wire, and it's going to be larger in the thin wire because it's a smaller cross-sectional area. We would like to keep the current constant, uniform throughout this piece of wire. So at the instant that this wire is connected to the capacitor, that's a very small instant, right after 0 seconds when the wire is connected to the capacitor. After a few nanoseconds or picoseconds, this electric field is set up. Now what this electric field is set up, now notice once again that in this complete circuit, E dotted with dl around the complete loop is still 0. It's a conservative electric field. There are no changing magnetic fields here. Now at the instant, right after we've connected the capacitor to the wire, this is one time scale. This time scale is of nanoseconds or picoseconds. This happens almost instantaneously. And we've learned that at the heart of this process is negative feedback. So by negative feedback, this charge redistribution takes place and an electric field is set up inside the wire. What will the electric field do? There's a sea of electrons inside the wire. What is this field going to do inside the wire? It's going to deliver a current. It's going to excite a current inside this circuit because J equals sigma E. So under the action of the electric field, charges are going to flow. Now this is a piece of wire and there's a gap here. The sea of electrons, if the sea of electrons flows in the anti-clockwise direction, charge has to come from somewhere in this region if the current has to be steady, for example. When under the action of this electric field that is set up, the sea of electrons is going to slosh forward with the drift velocity. And that sea of electrons is going to come from this negative plate. For example, the sea of electrons is going to move in the clockwise direction, opposite to the direction of the electric field. So electrons will rush outwards from this plate. They will rush outwards from this plate. And when they rush outwards from this plate, in this particular direction, the charge that is on this negative plate is going to be depleted. It's going to fall off. And when electrons are deposited onto this plate, the charge on this positive plate is going to fall off. So this capacitor is going to lose charge with time. So this initial electric field is instantaneously set up. This is the short time scale in this circuit. Then what's going to happen is that the current that flows under the action of this electric field is going to deplete the charge on this capacitor, and that is called the process of discharging. So after some time, so this is instantaneously after we've made the connection, say at some other time, t say of the order of milliseconds to seconds, if I were to draw the same diagram, if I were to take a snapshot of the electric fields and the charges on the circuit, what would I have is, I will have these parallel plates, I will have this piece of wire, a small section, now since electrons have flown out of this negative plate and gone onto the positive plate, the amount of negative charge on this plate has diminished a little bit, and the amount of positive charge on this plate has diminished a little bit. So the fringe field has gone down. Since the fringe field has now gone down, because the charge that's available on this plate is small, so its fringe field is going to be small. So now if I were to draw the fringe field pattern in this diagram, these vectors will still be pointing in the same direction, but the vectors will be smaller. Still, this vector is going to be larger than the vector here, but on average, all the vectors are going to be smaller in length. So the fringe field has gone down. The field inside has also gone down, because the charge on the capacitor has gone down. When the charge goes down, the fringe field goes down. Still, there is a distribution of dilution of charges. But the net charge on the surface is now smaller, which means that electric field is smaller. The charge gradient has decreased. So under the action of this electric field, the current now decreases. The current density goes down if the field inside the wire goes down. So with time, the current is steadily decreasing. Now if I were to plot with time the electric field, its magnitude of course, that's set up inside the wire, initially at time t equals 0, the field was maximum. At some point, say I choose a point P. At this point P, the electric field is maximum, and with time it's going to decay. Because charge is being depleted, the fringe field is decaying. Likewise, the current is going to decay with time. This is the current through the circuit, I, as a function of time. And furthermore, the charge on this capacitor is going to deplete with time. So everything is going to decay with time. This is the charge on the capacitor. So this process is discharging. Now initially the slope is large, and then slope just flattens out a little bit. So this means that initially the Q is large, and the decay, the derivative of this Q is I, remember. So Q is large, initially the current is large, which means that the decay of Q is large initially. Why is the decay of Q large? The decay of Q is large, which means that the current is large, because initially the electric field is large. So if this were a light bulb, initially when you connect this circuit, it's going to glow with full brightness, because it's the current that is delivering power to the bulb. So it glows with full brightness. But when it glows with full brightness, the current is large, which means that the depletion is large. The depletion is faster initially. More current is flowing through the circuit, charges are being depleted at a faster rate, which means that, and when the charge has been depleted, the electric field goes down, so the current goes down, which means that the rate of charge depletion goes down. So a bulb will initially glow brighter for a short span of time, but it will glow dimmer for a longer span of time. So what's going to happen if I were to plot with time the optical power of the bulb, which is just a fancy word for the glow of the bulb or the luminosity of the bulb. It's going to glow bright for a short span of time, then it's going to glow dim for a long span of time. Initially, the charge on the capacitor is large. Now this I is really minus dq by dt. It is the rate at which the charge of the capacitor is going down. Initially, the electric field is large because the charge of the capacitor is large. So the current is large. But the current is making the charges flow out of the capacitor rapidly. The large current makes the current large. So the depletion of the capacitor is large, is faster in the beginning. That's why the bulb glows in a brighter fashion. And then it becomes dim and keeps on dim and keeps its feeble glow for a longer period of time. So this is the action of the discharge of a capacitor. Any questions? This is very important to understand. Now we have a field description, an electric field description of how a capacitor discharges. And it's all connected to the kind of descriptions that we've already discussed in the previous classes. Of how, if this were a battery, what's the difference between this circuit and if I replace the capacitor with a battery? I give you half a minute to think about this and then I'll probe you. What's the main difference between a battery and a capacitor? Take a minute. रूमा अब तक ऊंची बोले. So the charge on the plates of a battery remains constant. That will remain constant. All right. So she's saying that for a capacitor, the charge on these plates is depleting with time. However, if this were a battery, and the battery also has two plates, consider a vortex cell, it has two plates, two electrodes, which has charge on it. The charge on the plates of a battery is not depleting with time. Roughly, yes, that is indeed the case. Because inside a voltage cell, there is a non-conservative form of work that is coming from somewhere. There is an external supply of energy. For example, in a Van de Graaff generator, it's a pulley that is moving a belt upwards. In a voltage cell, it's a chemical reaction that is taking place at the two electrodes. In motional EMF, it's the motion of a conductor inside a static magnetic field. And that power is coming from somewhere. So there is some external power. For a battery, we already know that we can define an EMF which is given by the work done by some non-conservative force inside a battery divided by the charge. So there is some non-conservative form of work that's going on which keeps the charge on these plates constant so that the current remains constant. But that's not the case for a capacitor, because for a capacitor, the charge on these plates is going to diminish with time. There is no source of energy that's available to replenish these charges. Replenish means to make up or atone for the lost charges on the plates of the capacitor. So a capacitor in one way is like a battery that is losing its electromotive force with time. Remember that there is electric field inside the capacitor. This electric field is large. This electric field is diminishing with time. So the source of power that is delivered to this resistor is this electric field. This electric field carries energy in it. Every field, be it electric or magnetic, is really energy. So when this field diminishes, the energy that is available to be delivered to this resistor is diminishing with time. So the source of energy here is the electric field inside the capacitor. And we'll find out how much is that energy. If you know what the electric field is, what's the energy per unit volume inside an electric field. We've already discussed magnetic fields in which we have a magnet, for example. And if this magnet produces a magnetic field, we know that there is going to be energy inside this magnetic field when we were discussing magnetostatic energy. So electric fields also store energies. They are reservoirs of energy, and there are huge philosophical debates on what kind of energy is this. Is the electric field just the energy, or there's something more to it? Anyway, this is how a capacitor discharges. And this is a rough argument of what the different parameters will look like with time. Remember, there are two time scales in this experiment. One is the time scale of feedback, when electric fields are set up inside the wire because of instantaneous charge distribution. Charge does not have to move from the capacitor to any point inside the circuit because charge is available everywhere. The sea of electrons is available everywhere. It's permeating this wire. It pervades this wire. It's everywhere. So an electron inside the sea just has to respond to local electric fields. And the electric fields are set up with the speed of light. So information is available all throughout the circuit instantaneously. So even though, so if you connect a bulb here to a charged capacitor, it will start glowing instantaneously. But then there is another time scale which corresponds to the discharge time. Current flows which diminishes the electric field. Now the electric field diminishes, and that happens at a longer time scale of the order of seconds to milliseconds, depending upon how large this resistor is and what's the capacitance of this capacitor. Alright, now this is how a capacitor discharges. I would like to leave this as an exercise for you to ponder upon. How does a capacitor charge up in the first place? Okay. So now consider a circuit like this. I'm not going to describe the circuit, but this is something for you to consider on your own. I have a parallel plate capacitor. Once again, it carries no charge on it. No charge. And I have a battery. And this is the positive terminal of the battery, so it has a reservoir of charge. This is a negative terminal of the battery. And then I have this piece of wire that connects to the one plate of the capacitor. Then I have a thin piece of wire which may correspond to a light bulb. And then this piece of wire connects to the other plate of the capacitor. This is my circuit. Right? Now, instantaneously, at time t equals 0 plus, this is a small gap d. There is really no charge on these plates. So there is no fringe field to the capacitor. But there is a dipolar field due to the battery. That dipolar field, this just looks like a continuous circuit. Alright? So this dipolar field that exists in all of space because of the battery is going to produce local electric fields. Those local electric fields are going to distribute charges on the surface of the conductor. So right at time t equals 0, there is going to be charge distribution which will look like this. It's going to be a high concentration of negative charge which is going to dilute with time. Then some positive charge is going to develop. This charge is going to go up. This is what it's going to look like at time t equals 0. This is going to set up an electric field inside the wire. Some small electric field here. slightly larger electric field here. Now this electric field is going to make a current go around the circuit. When this current goes around the circuit, what's going to happen is that electrons are going to flow in this direction. So this will become a positively charged plate because it will be depleted of electrons. Electrons will start flowing. When electrons will start flowing, these plates will become charged. And when they will become charged, an electric field is going to be set up in here. This electric field that's set up inside the gap will produce its own fringe field. That fringe field is going to point in this direction. So this is going to be a positive plate, negative plate. The fringe field is going to be in the opposite direction to the electric field that was initially set up inside the wire. So the field that was originally there is going to diminish with time. And that field is eventually going to come to zero inside the wire. So initially there was an electric field inside the wire due to the battery. But then as charge builds up on this capacitor because of that original dipolar field, that charge is going to produce a fringe field to the capacitor which is going to counteract the initial field. Eventually the field inside the wire is going to become zero. But then the charge has really built up on this capacitor. So now if I were to plot the charge on the capacitor, initially there was no charge, it's going to build up with time. If I were going to plot the current with time, will the current be larger in the beginning or at the end? In the beginning, because in the beginning there was no fringe field of the capacitor because there was no charge in the capacitor. There was all the field due to the battery. Okay? But then as the capacitor builds up charge, the blue field, which is the fringe field, is going to counteract the initial field. So the field inside the wire is going to diminish with time. So if I were to plot the electric field inside the wire, it's going to look like this. If I were to plot the current inside the wire, it's also going to diminish with time. So even for the charging of a capacitor, the initial current is large and then it diminishes with time. But charge builds up on the capacitor. So this is a field argument of how a capacitor charges and how a capacitor discharges. Now I've gone really fast through this argument. That's why I would like to take a small pause here, an intermission of a couple of minutes so that you can think on this own and you can reproduce my argument in your minds of how this field is developing. Remember, initially the yellow field, due to the dipolar field of this battery, which sets up charges and makes a current flow through this circuit, is large. But then that current deposits charge on this capacitor, which produces a fringe field which counteracts the original field. And the net field inside the wire diminishes with time. Just think about this on your own. And then we will mathematize this argument. Alright, now if I would like to mathematize this argument, I've drawn hand-waving diagrams here. They're pretty accurate. I would like to come up with a quantitative argument behind all of this. Once again, remember that all of the electric fields that we're talking about are conservative electric fields. Therefore, around this closed circuit, E dotted with dl must be 0. This is Faraday's law. around this closed path. Maxwell's equations are universal. They apply to electromagnetic waves, to optics, to electric circuits, DC circuits, AC circuits, whatever you can think of, they are universally applicable. So for this particular case, this holds true, which means that the potential drop across this circuit is zero, which is the Kirchhoff's voltage law. So now if the EMF of this battery is E, alright, suppose this is a resistor R, and all of this is a perfect conductor. Not a superconductor, but a perfect conductor. A superconductor is more than a perfect conductor, remember that. So all of this is a perfect conductor, which means that the resistance is zero of these connecting wires. Now this represents another voltage drop because there is an electric field. We've already learned that inside a capacitor or two parallel plates, there is a change in potential. That change in potential is given by minus E dotted with dL. Negative of the work done by the internal forces, which are the electric forces here. Okay? So there is a change in the potential. Now this E dotted with dL, we know that this is sigma over epsilon naught, roughly. If these plates are large or the distance between them is really small, you can approximate these as infinitely sized plates of capacitor. So this is really sigma, which is Q over A epsilon naught. dL is just the spacing d. This is the change in potential as we go from A to B. This is VB minus VA, which shows that everything here is positive. This shows that A is at a bigger potential than B. This is a positive plate, this is a negative plate. So this is the potential drop. So if you go around this circuit in this fashion, the electric field inside this battery, as you would all recall, is opposite to the electric field outside. So as you go around, you go from negative to positive, positive, negative, positive, negative. So this is the potential rise, this is the potential drop. And if you apply this Kirchhoff's voltage law here, you will get the EMF of the battery minus this potential drop, the magnitude of this potential drop, which is Q over this object, right? This object is called the capacitance, 1 over C. We define the capacitance C in the following fashion. The potential drop magnitude in a capacitor is given by the charge on the capacitor divided by the capacitance. It's a constant C that depends upon the geometry of this capacitor. Or the charge on the capacitor is C times the potential drop between the plates. It's the amount of C is really Q over delta V. It's the amount of charge that a capacitor can hold per unit potential difference across the plates. The amount of charge, it's like the reservoir capacity of a tank. How much fluid can a tank hold? Okay. So this, if we look at this expression here and we apply this Kirchhoff's voltage law, we have the EMF of the battery minus Q over C minus IR equals 0. Any ambiguities about this? You have to go around this loop, look at the potentials. You go from negative to positive, the potential goes up. You go from positive to negative, the potential goes down. Here the potential also goes down. Can you, for the sake of completeness, mention how this potential is going to change with path? If I take the variable x and I take the potential here, and I start off, say, at this point, C. This point is C. The potential is going up rapidly inside the battery. This point is D. Then it remains constant from D to A because this is a perfect conductor. It remains constant from D to A. Then it's going to drop inside the capacitor from A to B. Right? This is B. Then it's going to remain constant in this piece of wire. This is point G, this is point H. Then it's going to drop sharply from G to H. Okay? The slope tells us the electric field. The electric field is large inside the capacitor. Inside the capacitor is also large because the spacing is large. So the rise in the closed circuit has to be equal to the fall in the closed circuit. And at this point H, you have the same potential as where you started off from. You can move all of this potential diagram anywhere on the vertical scale. You can start from 0 as well. Doesn't matter. So this is the variation of the potential inside the circuit. So in a round trip, the change in potential is 0. And that's what the Kirchhoff voltage law is. That's what Faraday's law is. Remember, this is just a recap of old material. That's why I'm trying to go fast here. Now, if you look at this equation here, we would like to find out how does Q change with time. Ji Bilal.
Sir, if there will be a potential drop between G and H, then will the bulb glow?
Yes, it will glow because that is required. An electric field is required inside the bulb to make a current flow.
Even if they are at the same potential?
No, there has to be a potential drop here if the bulb is to glow. Because without a potential drop, there is no electric field. Remember, the electric field is the rate of change of potential. Without a change in potential, there can be no electric field. Without an electric field, there can be no current because it's the current that is delivering power to the bulb.
What I'm saying is that if the capacitor is at the same potential as that in the battery, then the bulb shouldn't glow. I mean, when the capacitor is fully charged.
Yeah, I'm not talking about what happens when it's fully charged. I'm going to do that in a minute. So look at this equation here. Can we solve this equation for Q? How does Q vary with time? Can you solve this for Q? Just make an identification that the current in this circuit has something to do with the charge of the capacitor. Where is that current coming from? Whenever current flows in this circuit, what's going to happen to the charges? When current flows, the capacitor will build up charge. So if a current flows in this circuit, it really means that charge is being deposited on the plates of the capacitor. Correct? When current flows in this circuit, and the current has to be continuous, when current flows in this circuit, charge is being built up on the plates of the capacitor. Otherwise, how can a current flow? The current cannot be discontinuous. The current has, if the current is steady, which means that the current, if you would like to have a good continuous stream of current flowing in this circuit, if you would like J to flow in this circuit, where will the current go? Current is the motion of charges. So when charges will flow and they hit this plate, they have nowhere else to go. So they will build up charge on the plate. So the current is really the rate of flow of charge, time rate of flow of charge. So the build up of charge is proportional to the current. That is just the current. I must equal the time rate of build up of charge. But then you might ask me the question, if current is flowing and charge is building up, and I've argued that the current is continuous, how is the current flowing through the gap of the capacitor? It's the changing electric field which is at equal footing as a current, as a conduction current. This is Ampere Maxwell's law. So as charge is being built up, the electric field is building up inside the gap. So this I will also be equal to epsilon naught times dE by dt. This comes from Ampere, Maxwell's law, from our last class. So there is a continuous current. Inside this conductive material, there is conduction current due to the sea of electrons. In the gap of the capacitor, there is no conduction current, there is displacement current, which is the changing electric field. That plays the role of a current. It's the same thing as the current. Now, this is I, it's the rate of change of charge. Now insert this in here, and I would like to solve this equation for Q. Could you solve this differential equation, please? तो इसको सॉल्व करो, कैसे करेंगे इसको सॉल्व? क्यों के लिए? इससे क्यों को कैसे सॉल्व करें? इंटीग्रेशन से पहले कौन ट्रिक इस्तेमाल करते हैं? वो तो कर लो, वो तो कोई बड़ी बात नहीं। तो है तो सही, लेकिन आपको डिफरेंशियल इक्वेशन को बनाना, डिफरेंशियल इक्वेशन बनाओ। गुड गुड। इसको Alright, so what we have is the following: E minus Q over C minus R dQ over dt equals 0. This means dQ over dt plus 1 over RC Q equals E over R. Now I multiply both sides by e raised to power t over RC, e t over RC, e t over RC. Then I realize that the left hand side is just the derivative of e t over RC into q, which is a function of time. Correct? Now this means that now I would like to take the integral of both sides with respect to t. So now I would like to take the integral of both sides with respect to t. Now this is the integral of a perfect derivative. So it just yields this term, e t over rc into q equals ec e into t over rc plus some constant of integration k. Now I divide both sides by e raised by t over rc because this can never be 0. And what I obtain is the following. My q of c, q as a function of time is e c plus k to e minus t over rc. Now I have to find out what this k is. If this capacitor is initially discharged, and this is the circuit that I'm talking about, if it were initially discharged, I had just touched the two plates of the capacitor with my hand and was standing on the ground, the capacitor discharged, then at time t equals 0, the charge is 0. That will set the initial conditions. The charge at time t equals 0 is 0. I'm given this. This means this equals EC plus K, which implies that K really equals minus EC. This would tell us that the charge on a capacitor is EC 1 minus E minus T over RC. Now I can plot this as a function of time. Time, the charge on the capacitor. What is this plot going to look like? And exponentially rising. At time t equals 0, this is 0, and it will rise up. When time is really large, after a large period of time, this thing goes to infinity, this thing goes to 0, and charge to some value. That some value is given by EC, which is the EMF of the battery into the capacitance. So the maximum charge that this capacitor can hold equals the EMF of the battery in volts into the capacitance of the capacitor. जो कुछ इसको मिल रहा है वो सब ले रहा है इस सूरत हाल में जब टाइम बहुत ज़्यादा गुजर गया इससे ज़्यादा कुछ ले नहीं सकता capacitor. In other words, the voltage on the capacitor in this case, this is the charge, the voltage is EC divided by C, which is equal to the EMF of the battery. So when the capacitor is charged fully, that really means that the voltage across the plates of the capacitor is equal to the EMF of the battery. And in this case, no current is going to flow. So this is the charge build-up. If I would like to plot the voltage build-up, it's also going to be exponential because the voltage is just the charge divided by the capacitance. So the voltage build-up on a different scale is, this is the voltage build-up, and the voltage will build up to the EMF of the battery. This is the voltage build-up on the capacitor. The electric field is also going to build up like this on the capacitor. So if I were to plot the electric field build-up, it's also going to be exponentially rising. Because the electric field is just the charge per unit area divided by epsilon naught. What about the current inside this circuit? It's going to be the derivative of this, right? It's going to exponentially decay. It's going to start off at some value and it's going to decay like this. You take this, find the derivative, you get a certain derivative. Initially, the current is going to be equal to E over R. This is the current at time t equals 0. and then it's going to decay exponentially. So this is the charging of a capacitor, and this actually matches the graphs that I've drawn here. This is the electric, this is the current, this is the charge, this is the voltage. The electric field is also going to grow with time. So this is what we have. We have the charging of a capacitor. Likewise, we can find the discharging of a capacitor. In the discharging cycle, our equivalent circuit is the one that we have over there. So if you solve that, you can write the Kirchhoff's voltage law, which really means that the charge on a capacitor, QT over C, which is the voltage on the capacitor, minus IR equals 0. Let's look at this more carefully. This is my capacitor. Now I'm drawing the resistor. I'm drawing a schematic diagram, a circuit diagram. This is Q. Positive, 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 negative, 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 negative. Now if I go around this circuit in this fashion, for example, this is a potential rise and this is a potential drop. So the potential drop is given with the negative sign minus IR. This is the potential rise. Now how do I solve this equation? I have to express I in terms of Q. For this particular circuit, what's the relationship between I and Q? Is I equal to dq by dt? It is minus dq by dt, because current increases when the charge is depleted. So for this particular circuit, I is defined as minus dq by dt. So I put this in here. Q equals minus IRC equals 0, which really means Q plus dq by dt RC equals 0, which means dq by dt equals minus 1 over RC into Q. Now I can integrate both sides, and my charge is E minus T over RC given some initial charge Q naught. Alright, I can differentiate this. I will get an exponentially decaying current. The charge on the capacitor is also exponentially decaying. Everything is going to match this rough plot that I drew without the mathematization. So this is how a capacitor would discharge. Initially, the current is maximum. Okay, and then it's going to drop with time, and you can look at the different ramifications of these solutions. You can look at you can plot different cases. Now what I would like to talk about in the last 15 minutes is the concept of capacitance itself. Now capacitance, as I've already defined, is the amount of charge that can be stored inside a capacitor per unit voltage difference across the plates. And we've also learned that for a parallel plate capacitor, C has been defined as epsilon naught A over D. Here, we've defined it here somewhere. This thing. So this is for a parallel plate capacitor. bigger plates compared to smaller plates will have a higher capacitance. They can store more charge for the same potential difference. Plates that are closer together can store a bigger amount of charge for the same potential difference. Alright? So this is what we have for a parallel plate capacitor. It's proportional to the area of overlap, and it's inversely proportional to the distance between the plates. And there's a constant here, which is the permittivity of free space. We're assuming that there is air or free space between the plates. Now let's look at some other kinds of construction and find out the capacitance for this material, for those devices. For example, let's consider a coaxial cable. We have an inner conductor that is positively charged. It's a long conductor. And then we have an outer sheath, which is a conducting sheath. No, sheath or a sleeve. This is negatively charged. And both of these conductors are uniformly charged because they're conductors. And they're perfectly symmetrical. Now if I look at the cross section of this object, this is what the cross section is going to look like. Inside we have air or vacuum. This resistance, this radius is RA, this radius is RB. Suppose that the charge per unit length is lambda. Okay, we already know what the potential difference between these conductors is going to be. We've already calculated that. Does anyone remember? If this is positively charged, this is negatively charged, the electric field is going to point like this. And it's going to be radially outwards. Remember, we used to draw these Gaussian cylinders. We can draw a Gaussian cylinder of radius r, and the electric field about the closed surface, which is E into 2 pi r into the length of this conductor, some section of length L. This is the left hand side of the Gauss's law. This equals the charge imposed lambda L over epsilon naught. So the electric field is given by lambda over 2 pi epsilon naught r. This is the magnitude of this electric field. Imran, sab theek hai? But why do we have an electric field? Because we would like to calculate the potential difference. This I am doing as a recap. I shouldn't be actually doing this, but never mind. This is the electric field. If I were to calculate VB minus VA, which I define as delta V, okay, this is B, this is A, this equals negative of the dot product of the electric field and this distance as we traverse it. So this equals minus lambda over 2 pi epsilon naught dr over r as we go from A to B. This is the potential difference between these plates. Now I move here, this is delta V equals minus lambda 2 pi epsilon naught natural log RB over RA. And I can take this minus sign into the log parentheses lambda over 2 pi epsilon naught natural log RA over RB. RA is smaller than RB, so this is a negative number. Of course, VB is smaller than VA because VB is at negative potential. But nevertheless, this is the magnitude of the potential difference. I can find out the magnitude. The magnitude will simply be this. The capacitance of this material, C, is therefore given by the charge stored. Now the charge stored depends upon the length of the wire you're considering. So the charge stored is lambda into L, the charge per unit length into the length of the wire. So longer wires will have a bigger capacitance, they can store more charge for the same potential difference. Of course that's the case. So this is a charge divided by this potential difference, which gives you lambda 2 pi epsilon naught natural log of RA RA over RB magnitude. This lambda goes away. You can find out the capacitance per unit length of this coaxial cable. That's 2 pi over epsilon naught divided by this logarithmic factor. So you can store bigger charge by making the capacitance can go up if this object is smaller. This object is smaller when log is smaller, which means that RB is large. When you make the outer radius large, it can store bigger amounts of charge. But that's not economically feasible because bigger amount of the outer conductor means you need more material. So you have to make an economic compromise. And an engineer is also an economist in the high side because he has to care about money. Nevertheless, the physicist will just give you a formula. So this is the capacitance per unit length of a coaxial cable. Let's look at another geometry. Is it all falling together? Are all the pieces coming up? Let's look at a large conducting dome. For example, a metallic sphere of radius r. Now, if you remember the Van de Graaff generator, on the top we had a metallic dome. It was a hollow from inside. When we're dealing with electrostatics, it doesn't really require to have metal inside. It's going to cost us money because all the charge is going to reside on the outer surface anyway. So the inner metallic interior of a conductor in electrostatics is useless. It might give mechanical stability, but it's electrically useless. Anyway, we have a metallic dome of radius capital R. Now, it stores a charge Q. One can easily find the potential of this object. The potential of this object with respect to infinity, if you remember, is given by Q over 4 pi epsilon naught capital R. So the capacitance of this dome, the amount of charge that it can store when it has been charged to a certain potential. And how is it being charged in a Van de Graaff generator? There is a belt that is moving upward. That belt is picking up charge because of friction between the belt and the pulley. This charge is moving up, and then there's a piece of conductor that is connecting to this dome, and it picks up charge by conduction, and this dome gets positively charged. So it develops a potential when it gets charged. Now we would like to see how much charge can it hold when it has been charged to say 10,000 volts. So that capacitance is given by Q over V, simply 4 pi epsilon naught R. So bigger the radius of the dome, the more charge it can hold per unit potential difference. If it's charged to 10,000 volts, a bigger surface can hold more charge for the same potential difference, for the same voltage. But look at this. If I touch this Van de Graaff generator, why am I allowed to do these demonstrations inside class? This voltage is really high. It's 20,000 volts, 30,000 volts. You saw sparks in the class. So it's of course greater than 50,000 volts per centimeter. So if I touch this, why don't I feel a current? The voltage is so high. The reason is that the charge is really small. Because the capacitance is so small. If I have a radius, say of 10 centimeters, which is 0.1 meters, which is a typical radius, this epsilon naught is so small that it keeps C small, it keeps Q small. The amount of charge is really small, and when I touched it, only that charge is available to constitute a current. So that charge per unit time gives me a current that is less than my perceptible threshold of sensation of feeling a current. It's less than, say, 1 milliamps perhaps. So I cannot feel that current. So even though it's a big voltage, it's a benign experiment because the capacitance is so small because of this epsilon naught here that it does not carry a sufficient amount of charge. The last point, what is the energy stored inside a capacitor? The energy inside a capacitor. There are different derivations for the energy inside a capacitor. Suppose the capacitor has been charged to some charge Q, which means that the potential difference V exists across it. Now I'm replacing delta V by V just for convenience. So there's positive charge here and there is a corresponding amount of negative charge here. So this configuration has potential energy because there's an electric field. Now if I would like, how have I synthesized this charge? I have a positively charged plate and I bring more positive charge to it. It gets more positive charge. I bring more positive charge to it. It's like constructing a charged sphere. I have a charged sphere, I want to build it up, I bring more charge, I gradually deposit more charge onto it. In other words, I'm transferring electrons from the positive charge plate to the negatively charged plate against the direction of the electric field. So I'm putting in more energy. Where is that energy going? Nothing is moving. That energy is going inside the electric field here. So if I were to calculate the potential energy due to this configuration, how much extra energy would I need to supply, dU, in order to bring a small amount of charge, dQ, onto this already charged capacitor? That's going to be equal to V dQ. Now this is the amount of additional energy that we need to bring in. So, as you know, U is generally given by QV. So if there exists a potential V, and I need to bring in some additional charge dQ, I have to supply this amount of extra energy. It's like synthesizing a conducting sphere. You've looked at examples of this kind. So this is the amount of extra energy that is supplied in order to deposit more charge on an already charged capacitor. But V is really equal to Q over C, dQ. So when it has been charged to its maximum, I can find out the small amounts of energy I had to make to construct this capacitor. So the total energy is going to be given by the integral of this. As I put in charge from 0, as it takes up charge 0 to a maximum value Q, I replace this Q by Q prime, doesn't matter. This gives me Q squared over 2C. This is the energy stored inside a capacitor. The total energy stored inside a capacitor. Q squared over 2C. This also equals half CV squared. If I replace Q by CV, I get this. The total potential energy of a capacitor is equal to half CV squared. And where is that energy stored? That energy is stored inside the electric field here. In the next class, I am going to derive another expression for half CV squared in terms of the electric field. In fact, let's do this right. It just takes a minute. Look at half CV squared, or let's look at Q squared over 2C. U is Q squared over 2C. Now what is Q? Q is sigma, the charge per unit area, into A squared over 2C. What is C? Epsilon naught A T. sigma squared A d 2 epsilon naught. Now what is the electric field inside the capacitor? The electric field inside the capacitor is sigma over epsilon naught. What is sigma? Sigma is epsilon naught into E. Let's put this in here. What I get is that the total potential energy is epsilon naught squared E squared AD over 2 epsilon naught. This is half epsilon naught squared into the volume of the capacitor. So the total energy into E square, of course. The total energy is equal to half epsilon naught squared E squared into the volume of the capacitor. The energy per unit volume given by small u is half epsilon naught E squared. So whether I have a capacitor or not, wherever there is electric field, the electric field carries energy, and the amount of energy per unit volume called the energy density borne by an electric field is given by half epsilon naught times the electric field squared. If there is magnetic field, it also carries energy. This is the electric energy. The magnetic energy is given by half. I replace epsilon naught by 1 over mu naught. I replace the electric field by V squared. This is the energy stored in a magnetic field. So when an electromagnetic wave comes and hits us as electric field, it carries energy with it and it carries momentum with it. Thank you very much. Let's reserve questions for post-class discussion. See you on Tuesday.